Okay, thank you so much. Thank you for the introduction. Thanks for having me here, and thanks everyone for coming. This talk is joint work with my students Seper Hajebi and Yanjali, and it's about list-5-colouring, which is NP-hard, and we classified which forbidden induced subgraphs make it easier. And as it turns out, it was only one class of forbidden induced subgraphs that was still open. So let me start by telling you definitions, and also throughout the talk, if something doesn't make sense, I'm happy for you to interrupt and ask questions out loud or in the chat or wherever is convenient. You can probably email me if you really want to. So this talk is about induced subgraphs, and induced subgraphs is a containment relation that's very strict. It means to get from G to an induced subgraph of G, the only thing you can do is delete vertices. So the only way you'll delete an edge is if you delete at least one of its ends, which means that, containing something as an induced subgraph is really containing that exact pattern. And if G does not contain H as an induced subgraph, we'll say that G is H-free. And I lost my pointer. I used to have a laser pointer. Let me take 1 second to find it. Here we go. All right, and throughout the talk, we'll look at forbidden induced subgraphs that are mostly paths and their disjoint unions. So PT is a T-vertex path. There's somehow disagreement whether the T denotes number of vertices or edges, but here it's always number of vertices. So P1 is a single vertex, and P3 is this, and then plus denotes the disjoint union of two graphs. And for example, I could write 5G for the disjoint union of 5 copies of G. And let me also tell you about list coloring. And again, something is a bit non-standard here, but let's go through it. So what 5 list coloring means, list-5-colouring, which is what I'll be doing throughout the talk, is that the lists of each vertex are a subset of 1 through 5. And in general, if K denotes the numbers 1 up through K, then a K list assignment means for each vertex in the graph, we pick a subset of 1 up through K, and that's his list. And then you probably all know what a K coloring is. It's an assignment of colors to the vertices from the set 1 up through K, such that for each edge, its 2 ends cannot get the same color. And it's an L coloring if the additional condition that for each vertex its color comes from its list is satisfied. So here's a 3 list assignment. As you see, it doesn't mean that lists have size 3, but actually that they're a subset of 1 up to 3, so they can have size anywhere between 0 and 3. And this is a 3 coloring of the graph, but it's not an L coloring because this vertex had list 2, 3, and it got colored red, which is 1. But this, for example, is an L coloring because you can see for each vertex, the color it ended up with is one of the colors in its list. And also for each edge, its ends get distinct colors. So just to sum up the problems we're considering, and the definitions are the following. There are 4 kinds of problems here. We could talk about coloring, which is you want to find, given G and K, if G has a K coloring. List coloring, where you're also given a list assignment. And then problems that are subtly different are those where K is part of the problem. So K coloring means that K is not part of the input, K is fixed, which means that here, if you had a running time of n number of vertices to the K, we would consider it a polynomial time algorithm for the third problem, but not for the first. Because in the third, K is fixed, it's part of the problem, not part of the input. And analogously in list K coloring, where again, K is fixed. And all of these are NP-hard if K is at least 3. So that's the starting point. And now my question, the question we'll be looking at throughout is, well, what if we restrict these 4 problems that I just showed you to the class of H-free graphs? What if we fix some small graph H and say, in addition to this input, I promise you that G is H-free, then is it still NP hard to solve these questions? And as it turns out, for coloring and list coloring, the answer is known. Those answers are given in these 2 theorems. For coloring, restricted to H-free graphs, we know that it's NP hard unless H is an induced subgraph of P4 or P3 plus P1. That's these 2 graphs. And for list coloring, the situation is even worse because it's only polynomial time solvable if H is an induced subgraph of this graph. So these are completely answered, and somehow the classes where it's actually easy are fairly small because including any of these things is quite restrictive. The situation is much different when K is fixed, because now running time into the K is acceptable, so you would expect that we can solve this for more classes of graphs. So since the answer is not quite as straightforward and not entirely known for all cases, let me define a notation for this situation. And what I'll do is I'll say that a pair H and K is good if K coloring can be solved in polynomial time on H-free graphs. And let me say that the pair is list good if list K coloring can be solved in polynomial time. Right, what I've told you so far is for the first 2 problems I showed you where K is part of the input. The previous slide gives a complete answer to when this is easy on H-free graphs. So now we're only focusing on the case where K is fixed, not part of the input. And then HK is good if with that fixed K we can do it for H-free graphs, meaning coloring, and list good if we can do list coloring. Here is a somewhat long list of things that are not good, meaning excluding this H still keeps things NP hard. And the first 2 things are when H is a cycle and when H is a claw, where a claw is this graph. So that's quite restrictive because that means whenever H contains a cycle or a claw, the pair HK is also not good. And since list coloring is generally harder than coloring, those pairs are also not list good. So which graphs H actually remain after just these 2 results? We have to have a graph H which doesn't have a cycle, so it's a forest, and it doesn't have a claw, so it's a forest of max degree 2. All that remains now, therefore, is disjoint unions of pans. And then here are some more results for pans of things that are not good, and don't remember these. I will tell you the ones that are relevant to the future later. But in particular, even when K is 4, we know that it's hard for P7. So the case where you just have one path becomes hard pretty quickly if you are trying to color with 4 or more colors. And we also know that when we have a disconnected graph with 2 components, then this one and this one are NP hard. So somehow this becomes hard pretty quickly, but there are a lot of open cases in particular. You'll notice that there's no hardness result here for 3 because we don't know any hardness result for 3 coloring. And also something that is not included here is when components are small, when each of the paths is very short, then none of these things help. We also know that this pair is not list good but we don't know if it's good. So if we exclude P2 plus P4 and we're 5-coloring, we don't know the answer, but if we're list 5-coloring, then it's NP-hard. And this is followed by an even longer list of things that we know to be good. 2-coloring is always easy, even with lists. And for 3-coloring, we have all of these results. They tell us then for patterns of length 7, or one of length 6 and the others of length 3, or one of length 5, the others of length 1, which is actually contained in that one, we can do 3-coloring. But this is where our knowledge ends. We don't know what happens for P8 and 3. And the other two kind of important results is this one and then this more general one, which says that if there's one component which is P5 or smaller and all the others are single vertices, then we can do K-coloring. These are all good pairs and list good pairs, except for P6 and 4-coloring, which is not list good. Which I think is actually the only case we know where definitely the answer for list coloring and coloring are different. Coloring we can do, list coloring we cannot. And now that I've given you a slightly long list of things we know, here's the table that is in every talk about this. If I only exclude a single path, not a disjoint union, then this table is drawn deceptively to convince you that we've pretty much answered this. In particular, if we exclude a path and we're doing K-coloring, then check mark means we can do this in polynomial time, X means it's NP-hard, and question mark is the only open case. So all the cases are answered except this one, which is of course actually an infinite open case, but this is pretty much answered except for this one thing, which appears to be very, very hard. Here's what we did, and I will tell you why it's interesting in a second. What I'll talk about is an algorithm for list 5-coloring restricted to RP3 free graphs, and just a reminder, this is what RP3 looks like. We can do this in polynomial time, so this is list good. And now let me walk you through this flowchart, which shows that this theorem actually solves the complexity of list 5-coloring when I exclude a single graph H as an induced subgraph. And then I'll tell you the proof of this result, because it's most of the time we'll not use 5, we'll actually use K. We'll go to 5 at the end, but most of it is K. So if someone could please figure out how to make the end of it also work for all K. Please let me know. But so first let me convince you that if you believe all the results on previous slides, that this actually answers the complexity of list 5-coloring H-free graphs. Because first we ask, is H a linear forest, which means a disjoint union of paths. And as we already saw, everything is NP-hard if we exclude something that's not a disjoint union of paths. Then we assume it is a linear forest and we ask, does it contain P6? But one of the first results I showed you is that 5-coloring P6 free graphs is NP-hard. So if H contains P6, then this is NP-hard because of that result. We can assume not. So then we ask, does H contain P4, 4-vertex path? If not, then each connected component of H is an induced subgraph of P3. So H is an induced subgraph of a disjoint union of a bunch of P3s. So we're polynomial time solvable, and if yes, then we ask, does H have at least 2 components that contain an end? If not, then H doesn't have P6, so the biggest component is P5 or less, and every other component is at most P1. And we're polynomial time because of this. And otherwise we have P4 and the second component with an N, and so is NP hard.
Sophie,
Yes.
could you expand the terminology linear forest?
Yes, a linear forest means a disjoint union of paths. So it's just a forest of max degree 2.
Oh, I see. Thank you.
Yes, good point. Should have said. This just means max degree 2. So if H is not a linear forest, that means it has a claw or a cycle, and therefore it's NP hard. All right. But yeah, this is surprisingly a lot of casework. And this is the thing I want to talk about. Okay. I'm going to start off by telling you how many of these polynomial time algorithms work in general. There's a framework that what we're about to do will fit into, which is if I want to solve something, I can assume there is a solution. Because if I have a big problem and I want to solve it and I make a bunch of modifications to it that make my life harder, and now there isn't a solution, but there also wasn't a solution when I started, then, I have not lost anything. So we're going to assume there is an L coloring and then restrict the instance a bunch and show that our restrictions are valid. If we had a coloring, then there will still be a coloring. And on the other hand, if what we put at the end has a coloring, then since it's just a harder instance than what we started with, the thing we started with should also have a coloring. How can we do that? Well, here's a stupid algorithm for coloring. Just take the graph, take your favorite vertex and try first to color it 1, and then try coloring it at 2, and then try coloring it 3, and solve the rest of the instance. Right? This is not a polynomial time algorithm, but it works because we know that one of the colors we give the first vertex will be right if there is a coloring. And so the procedure of doing such a thing we'll call guessing. So instead of saying try all colors of the first vertex and branch on it, I will just say let's guess the color of the first vertex. And as long as that branching procedure only creates a polynomial number of branches, we're okay. So in general, we can pick a constant size set of vertices and we can guess its coloring because we'll only branch into constant to the k, which is a constant number of colors of branches. In fact, I could guess a specific set. Like if you promise me there's a coloring where at most 10 vertices are colored 1, I could go through all subsets of size at most 10 and check, is this the set of vertices colored 1? And then color them 1 and remove 1 from all the other lists. This kind of stuff makes sense, but we're about to do it a whole bunch of times, so I want to make sure you're comfortable with the fact that this is allowed, we can do this, and it works if we do it right. All right. So there are 3 main steps. 2 of them, as I said, work for all k. The first one is we're going to reduce to frugal coloring, and let me tell you what I mean by that. If I have a coloring, if I have a set of lists for a graph and a coloring from those lists, I shall call it frugal if for every vertex, whenever a color is in its list, it has at most 1 neighbor of that color. Right, if I have a coloring and a vertex has list 1, 2 and gets colored 1, then it has no neighbors of color 1. But now I want to also put the restriction that it only has at most 1 neighbor of color 2. So here is the example from the first slide. That is just a 3-list assignment. And if you look at this, this is a coloring from those lists, but it's not frugal. Actually, for this vertex, it's okay, because while he has 2 red neighbors, red's not in his list. So that's acceptable. But this vertex has 2 blue neighbors and blue is in his list. So it's at this vertex where that coloring fails to be frugal. And now here, hopefully I computed a frugal coloring with this list assignment, because this vertex doesn't have 2 neighbors with the same color, nor he or he. This vertex has 2 green neighbors, but green is not in this list. And this has 2 blue neighbors, but blue is not in this list. So how can we make an instance have this kind of weird property? Here is a long lemma that has a lot of words, but instead of reading the words, let me tell you what it says. This is a lemma about hypergraphs, but we're going to think about it in terms of bipartite graphs. And it's an analog of the graph result that in a graph, you always either get a large matching or a small vertex cover. In hypergraphs, there's a third outcome that's neither this nor that. But let me tell you what the outcomes mean roughly. If I have a bipartite graph of bipartition A and B, such that every vertex in B has a neighbor in A, then one of 3 things is true. Either there's a small set in A, such that every vertex in B has a neighbor in that small set, say A prime. And by small, I mean constant. And also, I said this wrong, there's a small set in B such that every vertex in A has a neighbor in B prime, or there's a large set A prime with the property that no 2 vertices in A prime have a common neighbor in B. So the first one is the matching outcome, which here means more. It means that I have these vertices in A, a large constant number of them, and no 2 have a neighbor in common in B. The second means I have a small set B prime in B, and every vertex in A has a neighbor in that small set B prime. And the third outcome means that there is an induced subgraph of my bipartite graph, which is a 1 subdivision of KT. So I'm going to draw it as a non-bipartite graph, but it contains an induced subgraph that is a 1 subdivision of a complete graph, which means you take a complete graph and you put 1 vertex in the middle of every edge. And as you can see, that's bipartite. But also if you contain this as an induced subgraph, then you contain any path you want. And you contain RP3 if this thing is big enough, because you have a 1 subdivision, so you get a subdivision of any graph you want. Which means that when we use this, we always get the first or the second outcome. In our setting, if we look at a bipartite graph, such that every vertex in B has a neighbor in A, then one of these 2 things is always true. There are lots of vertices in A with no common neighbors in B, or there's a small set in B, such that everyone in A has a neighbor there. And when I say big and small, I always mean smaller than some fixed constant and bigger than some fixed constant. How is this useful? Well, we're going to use it to guess vertices of a certain color. If I look at a coloring of the graph like this, and look at the set of vertices colored 1 and the set of vertices colored 2, here is B set of vertices colored 1 and A set of vertices colored 2. I can look at the graph between them, and I can try to apply this lemma. But that's not quite enough. I will only use the set of vertices colored 2 that have 2 neighbors colored 1. Which, these are things I can't compute, right? I can't guess this because it might be of arbitrary size, and so guessing A and B is going to be hard. But what happens between these 2 has to be one of the 2 previous things. And now could it be true that I have a large set of vertices in A with no common neighbors in B? Well, A is the set of vertices with at least 2 neighbors in B. And the set of vertices colored 2 with at least 2 neighbors colored 1. So if I have a lot of vertices in A with no common neighbors in B, that's RP3. Right, if you look at this, each of them is guaranteed to have at least 2 neighbors. So that's RP3, which means I can assume that even though I can not compute the sets A and B, the thing that always happens between them is that there is a small set B prime, such that every vertex in A has a neighbor in B prime. So what we're going to do is guess B prime. And like I said, B prime is a constant size set. So we can try all polynomial number of possibilities for B prime and color them 1. And then what happens if I have a vertex in the graph that ends up being colored 2 and it has 2 neighbors colored 1, then it should have been adjacent to a vertex in B prime. So 1 should no longer be in his list. Right, if I have a vertex that will end up being colored 2 and it has 2 neighbors colored 1, then for the correct guess of B prime, it should have a neighbor in B prime, and so 1 should not be in his list anymore. Which we can repeat for all pairs of colors. This is what this line says. Right, we did this for colors 1 and 2, let's do it for all pairs of colors. And then for each vertex and every other color, if that vertex with respect to F had 2 neighbors of that other color, then that color is no longer in his list. For every vertex, if it gets 2 neighbors of a certain color, then it must have seen a vertex of that color in the set B prime we guessed. And so that color is no longer in his list. I'm saying it a few times because there's a lot to wrap your head around in terms of quantifiers, but this means that after we do this, in the branch where the guesses were correct with respect to F, we now only have to look for frugal coloring, because every vertex who saw 2 vertices of some color has no longer has that other color in his list. So in one of the branches, there's now frugal coloring, which means if we just look for frugal coloring in all the branches, then if there was a coloring to begin with, there's still a branch where we have to be successful. Because in one branch, we had to have made the correct guesses, and there, the coloring became frugal now. So from now on, let's look for a frugal coloring. And now let's make it even more frugal. I want to get rid of even more neighbors of a vertex that have the same color. And for this, I'm going to look at P3s in the graph. So if I have an induced subgraph, which is a P3, ideally, I want to get rid of all of them, but that's impossible, I think. So let me get rid of some of them. Let me say that if I have a P3, then I shall call it good if for every 2 vertices in that P3, their lists are not disjoint. So this P3 is good because every vertex in it has 1 in his list, and so no 2 lists are disjoint. This P3 is good because while there's no color in all 3 lists, every 2 of them have non-empty intersection. And this P3 is not good because these 2 have lists with empty intersection. And the point is that if I have a good P3 with some set of lists, I can guess its color. And I can guess a little more. And what we're going to do is take a good P3, guess its color, and a little more in such a way that every other good P3 with the same set of lists will have no edges to the first one. And if we guess a good P3 with some set of lists and everyone with the same lists has no edges to it, then we can guess another P3 like that and another. But since none of them have edges to each other, this has to terminate after our steps because we don't have our P3s with no edges between them. All right, so if I have one P3, what I can do is guess the coloring that this P3 will receive. And then for each color in the list of a vertex, I know that that color occurs at most once among the neighbors of that vertex. So for this vertex, I can guess either which vertex here is colored 1, or I can guess none of them are colored 1, which is a possibility. For this one, at most one vertex is colored 3, so I'll guess 1. And here at most one of its neighbors is colored 1, so I'll guess 1. And after having done this, I have guessed something of constant size, which I can because we branch into a constant number of subproblems. But now, all of these I know are not colored 1 or 2. None of these guys are colored 1 or 3. And none of those guys are colored 1 or 4. Because I guessed this vertex is colored 4, so none of these are colored 4, and he has at most one neighbor colored 1, and I guessed that it would be this one. Which means that after I had looked at this good P3 and guessed its coloring and these neighbors, the lists of what's left over here are disjoint from these lists. So if I have another good P3 with lists 1, 2, 1, 3, 1, 4, it does not use any of these sets, which means every other good P3 with lists 1, 2, 1, 3, 1, 4 that I'll find after having guessed this one will have no edges to this one. So after a constant number of steps, all of them are gone. And this doesn't hinge on the number 5 at all either. I just drew it here under the assumption that we were 5 coloring, but there is really no reason to use 5 over any other number. What happens if we have no good P3? Well, if you think about coloring, if you have an edge and the lists on that edge are disjoint, then that edge has no impact on coloring, right? You can never make it monochromatic if the lists on its ends are disjoint. So let me instead have a list at the good edges, which are edges where the ends don't have disjoint lists, the edges that actually matter for coloring. I can't delete the others because that's not an induced subgraph, but I can look at the graph of good edges and try to figure out how one should color it. And let's call ng of x the neighbors along good edges, meaning edges that matter for coloring. Now it's true that for each vertex, no two of its neighbors along good edges receive the same color, which is different from frugal because even colors that are not in the list of x aren't used on two different neighbors of x if those neighbors are along good edges. And let me tell you why. If we have two vertices here, meaning along good edges from x that receive the same color, well, here are those two vertices, say u and v, they receive the same color, then we know that the edge uv is not an edge of the graph because it's a coloring. They can't be adjacent if they get the same color, which means that if we draw uv and x, then it's actually a P3 in the graph, but it's a good P3 because u and v receive the same color, so they must have that color in common in their list. But x and u and x and v also have non-disjoint lists because we assumed they were neighbors along good edges. So if we go to the graph of good edges, which is the graph we're really trying to color, then for each vertex, no two of its neighbors receive the same color, which means if we're 5-coloring, then each vertex better have at most 4 neighbors in the graph of good edges, because no two of them get the same color. So if we have 5 neighbors, then the 5 neighbors and X itself use up 6 colors. And here's the step where we're really going to go to 5-coloring, but so far this is all true for all K. But now we're going to look more at what happens in the neighborhood of a vertex, and now 5 will make a difference. So here are a few simple things we can do with lists. If a vertex has list size 1, then it has exactly 1 color it's allowed to get. So we color it with that color and tell all its neighbors don't use that color. If a vertex has fewer neighbors along good edges than are in its list, then we can delete X, because if we color the rest of the graph, then we can put X back in, because it only sees fewer than are in his list colors that are in his list among his neighbors, right? This is the analog of saying if you're 4-coloring and the vertex only has 3 neighbors, then we can delete it and just put it back in later and say, let's give this vertex a color that isn't the color of one of his neighbors. In the same way for list coloring, if a vertex could never lose all colors in his list from the coloring of his neighbors, we can delete it. Also, as I said before, if a vertex has at least 5 neighbors along good edges, we're in trouble, because then we would use 6 colors, a different one for each of his good neighbors and a color for X itself. But also, another thing, if we have exactly 4 neighbors along good edges, then, oh no, it's not what it's saying. If X has list size 4 or 5, then there's something else we can do, because if you look at X, look at its good neighbors, and look at a second neighbor in the graph of good edges, then what is this? As it turns out, the list of X and Z have to be disjoint here, because if they have a color in common, this can't be a good P3. But the only way this isn't a good P3 is if this is not actually induced in G, which means that X is adjacent to Z. But if X is adjacent to Z and they have a color in common, then Z should be a good first neighbor of X, not a good second neighbor. Right, it's a bit roundabout, but if X has at least 4 colors in his list, then Z has to have list size 1, because for every second neighbor along good edges of X, the list has to be disjoint from the list of X. But if it has list size 1, then we would have already gotten rid of it. And therefore, if X has list size 4, then in the graph of good edges, this is a connected component, as we just said, of size at most 5. But we can color graphs of size at most 5, and therefore we just color this connected component separately and then delete it. Since it doesn't have good edges to anything else, this doesn't affect the color of anything else. All right. Now we're at the last step, and there are a few cases, but here's where we are. Every vertex has list size 2 or 3, because we got rid of list size 1 and list size at least 4. And what I want to do next is get rid of vertices with list size 3. If a vertex has list size 3, then we know it can't have at least 5 neighbors, and it can't have fewer than 3 neighbors. So it has 3 or 4 neighbors. And there are a few more things we can say about these vertices. here's X that has list size 3, and without loss of generality, let me assume its list is 1, 2, 3. Then I want to look at A and B, where A is the set of its neighbors along good edges that can be colored 4, and B is the set of its neighbors along good edges that can be colored 5. Then, as we just said, the second neighbors along good edges, which I'm going to call C, have list disjoint from X. So everyone in C has list 4, 5. And because of good P3s, we can conclude a bunch more things. In particular, A has to be a clique. There can't be a non-edge between two vertices in A because I would get a good P3, and the same for B. Also, if a vertex in C has a neighbor anywhere in A, then it's adjacent to all of A. And again, you can argue by finding good P3s. And the same for B. If there are two adjacent vertices here that have a neighbor in A, then if there were an edge here and they both had a neighbor in A, for example, then we would know that they're both adjacent to everyone in A, but one of them is colored 4 and one is colored 5 because the list is 4, 5. So nobody in A could be colored 4. Which means that we can remove color 4 from A. And also, for reasons of good P3s, if two vertices in C, that was the wrong button, if two vertices in C have a common neighbor in A, then they have to be adjacent or make a good P3. I'm going somewhat fast over this, but the conclusion of it is that C has size at most 2, otherwise we can make another reduction. And the way C has size at most 2 is actually A and B have to be disjoint, and one vertex in C is adjacent to all of A and the other is adjacent to all of B. In each other case, we can deduce that there are a bunch of edges and can deduce some reduction in lists. That helps us out. If C has size 1, then it's a cut set, like a cut vertex, right? Because this is all second neighbors along good edges of X. And if we have a cut vertex and a component on one side of bounded size, we just check which colorings of this vertex extend to this component and then reduce the list at the cut vertex accordingly. Which means we can assume C has size exactly 2. And now there are two cases, right? We said X has 3 or 4 neighbors. 4 neighbors is easy because if you have exactly 4 neighbors, this graph has 5 vertices, all of different colors. And this is the set of all vertices that can be colored 4 in the set of size 5, which tells us that here, some vertex has to be colored 4 because we have 5 vertices, all of different colors. One of them has to be 4, and this is the only ones that can be colored 4. And one of these has to be colored 5. But then we know that A should be colored 5 and B should be colored 4. And so we've reduced lists. And finally, the last case is the case of 3 neighbors. So now X has exactly 3 neighbors. C has size exactly 2. It looks like this. And now I can still ask which colorings of A and B extend over to X. I know that coloring this 4 and coloring this 5 does not extend because then I have 4 vertices here and nobody can be colored 4 or 5, and yet they should all get different colors. So I can assume this coloring doesn't extend, and there are 4 more. If the coloring 4, 4 also doesn't extend, then I can remove color 4 from A. If the coloring 5, 5 doesn't extend, then I can remove color 5 from B, because coloring B5 will never work. So I can assume that those extend. And finally, I can also assume that the coloring 5-4 extends, because that doesn't actually remove any colors from the left-hand side of the picture. So if that coloring doesn't extend, then none of them work. And last step, I promise. Now we have this behavior. We just want to let the rest of the graph know that the left-hand side of the picture is happy with anything except coloring A4 and coloring B5 at the same time. So what I'm going to do is I'm going to look at a neighbor of A and a neighbor of B here. And there are two things that can happen for these vertices, right? They could have, we know that the top one has a 4 in its list and the bottom has a 5 in its list. Now they could have another color in their list in common. So then one of them might be 1-4 and the other might be 1-5. And it might be 1-4 and something else and 1-5 and something else. Or they might have disjoint lists. And so I can assume one of them might be 1-4 and one of them is 2-4. And what I want to do is transform this left-hand side picture into the right-hand side picture. If this has a 1 in its list and this has a 1 in its list, then because it doesn't make a good P3 with X, these two are adjacent. So if they both have 1 in their list, then I can delete some stuff and reduce some lists and create this as an induced subgraph with lists that are subsets of the original lists. And on the other hand, if one of them has a 1 in his list and the other a 2, then let me also keep X. And let me keep this much of the graph, where there might be an inch here and I don't care. But the point is that what I'm keeping is an induced subgraph. So I still don't have good P3s or anything else because all my reductions remain valid since I'm going to an induced subgraph and a graph where the lists go to subsets of what they were before. And for the last step, we need to check that both of these things, in fact, model the behavior. Everything extends except making A a 4 and B a 5. But you can convince yourself that if you color A and B with 4 or 5, the only way it doesn't work is if A is a 4 and B is a 5. Right? In each case, you can check that this coloring gives us a problem, but if you make one of them not be the problematic color, then you can color this one, for example, and it'll extend, or color the other one. So I mean, there's a bit of checking and I'm going to skip it, but these two actually model the exact same constraint as the previous component, which is every coloring of AB works except making A a 4 and B a 5. And now we had a vertex with list size 3 and it's gone, and we haven't guessed anything. Right? We've reduced this using arguments that didn't involve guessing any color. We got to frugal, we got rid of good P3s that involved guessing, but getting from list size 3 to list size 2, no guessing, so we can do this everywhere. And then the last thing is, if you look at list coloring and all lists have size at most 2, we can always solve such instances because it's 2 satisfiability. If every vertex has a list of size 2, then you just say for every vertex, X is colored 1 or X is colored 2, and for every edge you say X is not 1 or Y is not 1, and this way you can model it using 2 satisfiability and solve it in polynomial time. And that's it. We use that to do the last step. So frugal, you can do with any k. Good P3s, you can do with any k. And then somehow the last step where we're really looking at the details, we need something else to handle k bigger than 5. Also, oddly, this solves the question for list 5 coloring with one forbidden induced subgraph. Because we can't do this algorithm for k bigger than 5, it doesn't solve 6, 7, 8 coloring. But also because of different NP hardness reductions, while this algorithm works for 4 or 3 colors, we don't have a complete answer there yet. So list k coloring with one forbidden induced subgraph is only solved when k equals 5, not for smaller numbers, not for bigger numbers. Isn't that strange? Please solve one of the other cases. Usually fewer colors is easier. Why do we only know the number 5? What's special about 5? And on that note, let me not show you NP hardness reductions. Thank you so much for coming to my talk.
Thank you, Sophie, for the very engaging talk. And if you can, let's unmute and clap for Sophie.
Thank you.
Thanks. Let me stop recording now.